Okay, let's turn on the recording. So we will go ahead and collect homework today. I still wanted to at least mention a couple of the, the problems that we hadn't had a chance to talk about, at least discuss in class, right? I guess I need to try to write down the solutions or something like solutions to post these. So I'll think about that, okay, when I'm going to try to do that. Before we look at just one or two extra of those homework problems, so I'd like you guys to share your solutions, primarily, at least in class. Like I said, I can post solutions eventually to the homework. I did not on the homework number 2. I was asking before class. I don't think I put a copy on Blackboard of a Xerox of the text problems, but I can do that. So I'll try to make a copy of the homework 2 problems that are in the that are from the text. Okay. For that second homework, so that you can refer to that. Okay, so we were discussing this problem last time, and I wanted to write down the solution to this and show you how we can find a solution to this, because it does illustrate an important technique that we're going to come back to later in the semester for counting sets. Kind of an advanced technique. Today, as soon as we finish these notes and talk about the homework, we're going to get into the elementary counting techniques. So up until now in the class, we've sort of just been relying on our sort of brute force intuition, right, to answer questions. Brute force intuition and logic, and sort of exhaustively examining possibilities. Maybe not exhaustively examining possibilities, but kind of exhaustively examining all the possibilities, all the elements of a set, right? Or all the possible elements of a set in order to count a set. But today we're going to look at, start looking at how we can, systems that we can use, methods that we can use to count sets a little bit more, in a little bit more rote way, a little bit more systematic way, okay, than just, always starting from scratch in counting sets. But we're going to begin with really elementary methods so that you're probably, that are very intuitive, so they'll either seem familiar to you, or but perhaps they really are familiar to you from past classes. But the technique that we use to answer this question is not is a little bit more advanced. Okay, so remember, this is a problem from combinatorial geometry. So geometry is often a setting for combinatorics problems. Sometimes they're really fun and interesting problems. Geometry problems are often interesting, and combinatorial geometry problems are especially interesting. But here's a very simple example. So suppose that we are going to draw some, so we started this last time, right? Suppose we draw some lines in the plane, right? So we have a set of lines, and so this can be any number, and we want to count then how many regions that those lines divide the plane into, right? How many distinct regions there are surrounding or between the lines, okay, once you've drawn them. The one sort of condition that's really important to help us analyze the problem, make it a little bit easier, is we want the lines to be drawn in general position. So general position means, you're going to hear that phrase a lot in geometry. Something is drawn in general position, and that means different things in different situations, okay? But usually it means they're drawn in the most simplified way, right? Or the way that makes the problem easiest. In this case, general position for drawing these lines means that they're not parallel to one another, and not more than two intersect in a single point. Now, if they're not parallel, they have to intersect, but you don't have multiple lines intersecting, more than two lines intersecting in the same point. Okay, so that makes the problem easier to analyze. All right, so that's the basic counting problem. Set is going to be the number of regions formed by the lines, right? Okay, and of course the set L changes, right, when you draw different numbers of lines. Okay, and we just want to count that set. Obviously, that set's going to be non-empty, right? Okay. Even if you don't draw any lines at all, the plane itself forms one big region. So even if if n is equal to 0, L is not empty. It's 1. Okay. So interesting question here is not is just the set not empty, and sometimes we're just interested in answering that, right, when we're trying to find the cardinality of a set. Just is it more than 1? But in this case, it's obviously more than 1, right? So last time, just by some experimentation, it's easy to draw a few lines and count the number of regions, right? So we just experimented right last time, and we saw that if n is 1, then there are 2 regions. That you don't even have to draw the line, right? You can do that in your head. If n is 2, you can do that in your head as well, right? You see the number of regions is going to be 4. It's a little bit harder to do it in your head. If n is 3, okay, so that you probably really do have to draw and count. But we did that, right? So if n was 3, it turned out that the number of regions is 7, okay? And if we did that right, okay, this is what everyone sort of agreed on, so I'm assuming that we did it right. And then we got up to if n is 4, the number of regions was 11, all right? Okay, so there we were just using brute force logic, right? Or just examining the set, right, and counting in the most elementary way, right? Just 1, 2, 3, 4, just numbering off the regions, correct? Okay, so that's just naive counting. That's first grade counting procedures, right? Okay, if n gets very large, then our first grade counting procedures, right, are not going to work, right? And so we want to see if we can come up with a more general method for finding the size of L, right? For large values of n, or perhaps for arbitrary values of n. So perhaps we can develop a formula for what the cardinality of the n is going to be based on that number of lines, correct? Based on the value of n. That's actually what we want to do, okay? All right, so let me show you now how we're going to solve that counting problem, okay? So here's the suggestion, and you actually used a very similar idea in one of the homework problems, right? Okay, when you were trying to count the number of tilings with dominoes of a 2 by n chessboard, right? Remember, we developed this formula that related that number of tilings to the number of tilings of a smaller 2 by n chessboard, correct? Okay. So that was the formula that we suggested last time. Okay. All right. Well, so we're going to come up with a similar formula here. What we want to do is see if we can figure out the value of the size of L for a particular number of lines k. So I'm going to call that L sub k, so I don't have to keep writing down, L with the vertical bars, right? Okay. So L sub k will be the cardinality of k when the number of lines is exactly k. And I want to see if I can find an equation that relates L sub k, the number of regions when the number of lines is k, to L sub k minus 1. That would be the number of regions when the number of lines is 1 fewer, right? When the number of lines is k minus 1, okay? All right, so that's my goal here. And if I can come up with such an equation, that's called a recurrence relation, all right? And once we've developed a recurrence relation, you can see they're really handy tools for helping us count the size of sets, okay? And they're really going to be handy here, all right, in this particular situation. All right, so let's see if we can devise such a recurrence relation. And if we think about it carefully, or just right maybe, I'm not sure if carefully is the right term, but if we think about it just right, this recurrence relation is not that hard to develop, okay? So let's imagine that we've already got k minus lines there drawn on the plane, okay? We've already got k minus lines drawn on the plane. All right, so those lines are just in general position, right? So they're sort of going all over the place, right? But remember, they're not what? parallel, right? Okay, so one thing is they're not parallel, and then they don't intersect in multiple points, right? Okay, so let me imagine I'm drawing k minus 1 of these lines, okay? Of course, I don't know what the value of k is here, but so the number of lines here is kind of indistinct, but they're all coming all over the place, right? Yeah, okay, but they're not, remember, they're not parallel, okay? Now, of course, I haven't drawn the full plane here, right? So you don't have the full picture because these lines are not parallel. So they're gonna, all of them are gonna intersect eventually, right? Did I draw any that were accidentally parallel? Maybe. All right, okay. These two look like they're almost parallel. Okay, but they're not. All right, so just assume they're not parallel. All right, so those two are going to cross each other eventually, maybe somewhere down here, right? But it's out of my picture, okay? All right, now, so that's k minus 1 lines, all right? And what I want to do now is add in the kth line, right? Okay, I'm going to add in the kth line. Now, let's imagine. Now, of course, the kth line can go any darn direction, right? But let's imagine that when we add the kth line, we're going to orient the plane. So we're going to rotate the plane if we have to, so that the kth line appears that it is horizontal, all right? And that's certainly not necessary, but that's just going to help me sort of visualize the situation a little bit better, right? So when I come in to draw that kth line, no matter what its actual slope is, I'm going to think of reorienting the plane, right? Just rotating the plane so that that kth line is horizontal, okay? All right, so in other words, when I draw the kth line in here, it's going to come across here as horizontal. Now, of course, what's it going to do eventually? It's got to intersect, yeah, it's got to interact with all these other lines. It's got to intersect every single one of them, right, okay, because it's not parallel to any of these, all right? So let's imagine that we're just going from left to right, okay? Let's imagine that we're just going from left to right here, okay, and we're thinking about what happens when that that kth line intersects the previous k minus 1, right? Okay, lines, all right? So we're coming across here, and then we come into the first one there that it crosses, right? Okay, from left to right, all right? So it touches that one, right? Okay, and then somewhere it's going to hit this one, correct? The next one, and then the next one, and then so on and so forth, right? And then eventually it'll get past all of the other lines, right? And sort of continue out here in, this big blank space over here on the right, okay? All right, so y'all sort of in agreement, right? That's what's going to happen, okay? Now, I've drawn it here in kind of a very easy to analyze way, right? Okay, so the picture may be a lot more complex than this, right? But the part about being horizontal is really not a simplification on my part. All I did was just rotate the plane, okay? So I can certainly draw the picture so that the kth line appears to be horizontal. All right, now let's see what's happened to the number of regions, okay? So remember, when we had the k minus 1 lines, we had a bunch of regions, okay? Now look, don't confuse yourself here. Don't think when you had k minus 1 lines that you just had 1, 2, 3, 4, 5, 6, 7 regions, right? Okay, you had more regions than that because what's happening to these lines outside of the picture here? They're intersecting, right? And when they intersect, you start getting more regions, correct? Okay, so don't mislead yourself about how many regions you're starting with when you add in this new line. But what's going to happen now to all of those prior regions when you add in the new line, okay? So let's think. We're coming from left to right, okay? And we hit this first line that we're going to intersect with, right, from left to right. And what happens to this region over on the left? It gets cut in two, right, okay? So you get now an additional region, okay? So notice when you cross this line, you get an additional region. Now you keep going and eventually you hit the second line, right? And what happens to this region? It gets cut in two, right, okay? So you get a new region for when it hits this line, right? And then you keep going to the right and eventually you hit this line, correct, right? And what happens to this region that it's passing through? It gets cut in two, right? Yeah, it gets cut in two. So you get an additional region, right? Okay. So notice as you're going from left to right, okay, you're passing through a region on the left, right? But every time you hit one of those lines that was already drawn there, see, I'm thinking about I'm drawing that new line, correct? So it's passing through a region from left to right. Every time I hit one of my pre-existing lines, that region on the left gets cut in two. So in other words, you get an additional region, right? So how many additional regions are we going to form here when we draw in the kth line? Well, you're going to get one when you hit this one, 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 one when you hit this one. What happened? How many is that so far? Well, it's k minus 1 because it's the same as the number of lines that you had drawn there, right? Remember, I didn't put it here, but I didn't make a note of it. But remember, this is k minus 1 lines, right? So we've already got, every time we hit one of those original, one of those pre-existing k minus 1 lines, we get another region, correct? So we get k minus 1 new regions, but I lost track of one because there's one additional one also. Remember, this is the kth line, right? So so I get k minus new ones, but there's one more. What's the one more? Okay, so remember you're going from left to right here. You get a region when you hit a new region when you hit this line, 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 new region when you hit this line. But eventually here you'll travel out into space here on the right, correct? Right? When you're past all the lines, that also is a region, correct? What's going to happen to that one? It also gets split in two, right? Okay, so you get a new region for all the pre-existing k minus 1 lines plus what? One more, right? Okay, the region on the far right also gets cut in two. Okay, right? So we actually get k minus 1 new regions when we draw the kth line plus 1. Okay, all right. So that's really the clue. All right. So now I can write down my formula for L sub k. Remember, this is the number of regions when I have k lines. So the number of regions when I have k lines is going to be what? It's the same as the number of regions when I had one fewer lines, correct? Plus, what happens when I add the kth line in? How many new regions do I get? You get what? K minus 1, correct? Right? One for each of the previous lines, but plus what? Plus one extra, right? The one here on the far, the region on the far right gets cut in two. Does that make sense? Are y'all following me? No? Okay. All right. So remember, this is number of regions, right? Okay. This is number of regions. So the number of regions when I draw the kth line is the same as the number of regions when I had the previous k minus 1 lines plus k minus 1, because that's the number of old regions that get cut in two, plus one additional one, this one on the far, this one over here on the far right that gets created. Ah, there's my formula. That's it, okay? That is a recurrence relation because we can count the number of lines, the number of regions when I have k lines based on the number of regions when I have k minus 1 lines, okay? Now, how can we use that recurrence relation, okay? Well, we have to use it a little bit slowly, Eduardo, okay, right, okay? Because I cannot jump in and say, okay, now I want to compute the number of regions when I have 100 lines, okay, right, okay? I mean, we can write down the formula in that case. So the number of regions when I have 100 lines, right, would be what? Well, that would be what? The number of regions when I have what? How many lines? 99 plus what here? 99. These two things are the same, notice. Plus what? Plus 1, okay? Unfortunately, that's about as far as I can get, right? Okay? Because I can't figure out exactly what this number is, because what do I not know here? Yeah, I don't know L99, right? Okay? So to compute L99, what are you going to have to do? Yeah, then you have to step back, right? Okay, and you're going to have to write the formula for L99, right? Okay, so you're saying, okay, now I need to know what this is. I have to write down the formula for L99. Bummer. That's what? Oh, that's L98 plus what? 98 plus 1, right? Okay. So, well, of course, eventually, if you work far enough back here, if you work far enough down this, if you work far enough down this sort of chain of equations, eventually you'll arrive back at what? Yeah, you'll end up with L of 0, right? Okay, yeah, okay. But you know what L of 0 is? That's what? 1, right, okay. So you know L of 0 is 1, right, okay. And then what can you start doing? Start filling in the values backwards, right, until you get back up to L100. So it's going to be a little bit of work, right, to actually compute L of 100, right? Because I got to write down all these equations, and then I get down to L0, and then I have to go backwards, right, filling in all the values. But I could do it, right? Okay, I mean that's a systematic method for doing. It may be easy to program this, right? Okay.
Or an Excel spreadsheet.
Or an Excel. Well, that's programming it, right? Okay. So same thing, right? So at least we can answer the questions eventually if we were just desperate to know what L of 100 is. But what I'd like better is what I'd really like is a formula for L sub k, right? That depends on k, where I don't have L sub k minus 1 in the formula, right? So I would just like a formula for L sub k that's just a function of k, right? So some formula involving k that doesn't require me to compute L sub k minus 1. Well, now let's see if maybe we can figure that out. Maybe we cannot, but maybe we can, all right? So that's our next goal here. Let's see if we can figure out a what's called a closed formula for L sub k, all right? That's not a recurrence relation like this one. All right, but we better check this. To develop that formula, I'm actually going to check this recurrence relation, okay? So because I'm not even sure this is correct, right? Maybe my geometry was off, right? So I haven't verified even this. I haven't verified it all, right? Okay, so we're going to try verifying this a little bit, and the way we can verify it is the fact that we already computed up here some of the small values, right? Okay, so let's apply the recurrence relationship to some of the small values. So we already know L sub 0 is what? 1, right? Okay, all right. Now let's figure out L sub 1. Now I already know this is what, of course. Yeah, I already know this is 2, all right? So that I just counted by, just inspection, all right? So I already know that's 2. But let's see, does the recurrence relation work? Because the recurrence relation says this is what? L sub what? 0 plus plus 0, right? Plus what? Plus 1, right, okay. But what is L sub 0? 1, right, okay. So you get 1 plus 1, cool, all right. Yay, that worked, okay. So that makes us feel a little bit better. But, L0 and L1, those couldn't be very large values to start with, right? So even if we were just making up numbers here, we'd have a very high chance of, even if we gave this to a elementary school student, right? They would if they just guessed, they would have a very high chance of getting these values right because they're just small values, right? Okay. So let's keep going here. All right, just to check it a little bit further. So what's L sub 2 now? Yeah, it's L1 plus what? What'd you say, Dalton? 1, right? This value repeated, right? Okay, and then plus, you always have this 1. Oh, by the way, I wanted to, y'all are probably thinking, I could have simplified this formula, by the way, but I didn't for a reason. But, of course, you can simplify this recurrence relation. What is this? This is L sub k minus 1 plus what? What's k minus 1 plus 1? Yeah, that's just k, right? So I could have written it down this way, but I didn't do that for a reason. Okay, all right. I left it as k minus 1 plus 1 because it's going to make my further analysis easier. All right, okay, so I had a little secret there and not simplifying this. Okay, I should have made that clear earlier. All right, so this is L plus 1 plus 1, right? Okay. All right, but this, of course, let's see, is, but what was this one? 2, right? Okay. So we have, oh, no. Let me see if I'm, this is, that is 2, right? Okay. And so these add up to give me 2, right? Okay. But L sub 1, remember, what was it? What was its formula? It was this, right? Which is 1 plus 1. So I'm writing it in a particular way. Of course, when you add 2 plus 1 plus 1, what do we get there? What's 2 plus 1 plus 1? I'm boggling y'all, I can see, because you're not answering that. What's 2 plus 1 plus 1? 4, right. Okay. All right. Look, here's what I did. All right. I added these two things together, okay, and then I wrote that as 2. All right. So I added the 1 plus 1, and I wrote that as 2. And then remember, what's L sub 1, though, from the prior line? It's 2, but here's the computation that gave us 2, right? It was 1 plus 1, all right? So I'm going to fill in, for L sub 1, I'm going to fill in 1 plus 1, okay? Again, I'm doing that for a reason, because there's a pattern here that I want to detect, okay? All right? So remember, that's how L sub 1 was calculated. It's just 1 plus 1. All right. So, but do we get the right number there? 4? Yeah, okay, so the recurrence relation worked, all right? We got 4. All right, now let's try L3. But again, I want to try to analyze it in this way. So what's L3 there? What is that now? L2 plus what? Plus 2, right? Plus what? We always get the plus 1, okay? Now, how am I going to rewrite that? Okay, look. Take the 2 plus 1 and add them together. What does that give you, of course? 3. Now, what was the addition that gave me L2? So go back up to this line. What's L2? 2 plus 1 plus 1, right? Okay. All right, let's try it once more, and I think you're going to see the pattern here if you don't already see it. So L sub 4 is what? L sub 3 plus what? Plus 3 plus 1, according to the recurrence relation. But what is this number? 4. But how was this calculated? Go back to the previous line. So that's what? 3 plus 2 plus 1 plus 1. Oops. You seeing something here now? Okay. So in general, okay, what would L sub k be equal to? Look at that sum. Of course, it's going to be L sub k minus 1 plus k minus 1 plus 1, right? Okay? But how does it appear that's going to simplify? So we'll get what? K plus what? Plus k minus 1, correct, plus, yeah, plus k minus 2 all the way down to this 1, right? So you'll go all the way down to 1. And then, what do we have added on at the end? Yeah, 1 additional 1, okay? See that? That now before I answer your question, Kaylee, that now, notice, is a formula for L sub k that's not a recurrence relation, you see, okay? I mean this, the right-hand side. That's a formula for L sub k that's not a recurrence relation. It just involves k. It does involve k, but it doesn't involve L sub k minus 1. That's what we were after. Yeah. Where? Oh, yeah, I did, didn't I? Okay, so that was wrong. Yeah, it's this subscript repeated, right? So that should be k minus 1. So that's nice. So see, now we have a non-recurrence formula, right, for L sub k. Now, I'm going to make it even better because we have this sum involved in the formula for L sub k, but that's a very familiar sum, all right? So I think we already discussed it, didn't we? Okay, here is the sum from adding the first k positive integers together. This sum occurs frequently, okay? And so there's actually a shorthand, a simple method for computing that sum, okay? There's a very famous story that you probably heard before involving that sum, okay? But it's just, of course, I'm reading it backwards here. So it's 1 plus 2 plus 3 plus 4, all the way up to some positive integer k. And so we have a shortcut method for computing that sum. Do y'all know what short? K times what? K plus 1. Yeah, right, over 2. Yeah, okay. So if you don't know that, we've mentioned that formula already in the class, I think, when we were finding the magic sum of a magic square. But here it is again, okay, because it pops up frequently. So 1 plus 2 plus 3, that's going to be whatever your final integer is in your series, plus 1 more times 1 more than that, and then divide by 2. Okay, and then, but don't forget, this plus 1 was just hanging on there. All right, so we have to add that in as well. So if y'all want to, I guess y'all can simplify this. You could add the 1 in here if you want to, but we could leave it like this as well. So so there it is. There's our formula for that number of regions. Cool. Okay. Do y'all know the famous story of this sum? So Gauss is a great mathematician, Gauss, from the late 1700s, but primarily the early 1800s. So Gauss is one of the big three of mathematicians. They're usually ranked one of the top 3. So that would be Gauss and usually Newton and Archimedes. Okay, so Archimedes. So people don't give Archimedes. Most people don't give Archimedes such credit, but he ranks as one of the top 3. What? So. No, that's Euclid that wrote the element. So Euclid, unfortunately, does not make the top 3. Okay, but anyway, Gauss is one of them, and so Gauss was, a prodigy, and so when Gauss was a little kid, but this is probably, maybe Gauss tells this story, so maybe it's not just a apocryphal story. But anyway, Gauss was an elementary school kid, and the class. According to this story, which again might be embellished, the class that day was being particularly unruly. So the teacher was, frustrated with the class. So to get them to quiet down, the teacher asked them to add up the numbers 1 to 100. Okay, and so thinking that would occupy them for a long period, right, to settle them down. But then Gauss came up within like a minute and said, "Okay, here's the answer. I'm done." Right, and apparently got punished for that for being impertinent, with the teacher and answering it so quickly. It was the right answer. But Gauss knew this formula, right, or actually on the spot apparently developed this formula with a very clever way of seeing why that formula is correct. Okay, all right, so. Anyway, that's that formula. So there is our formula, okay, for that number of lines. So let's see, what is L100 then? So now we know it, right? It's what was that? 100 times 101, right? Over 2 then plus that lonely extra 1, right? Okay, so 50 times 101 plus 1, that's the number of regions we're going to get there. Okay, nice. All right. Somewhere, either on a test review or in future homework, I'll see if I can find some other nice, I have some in mind, combinatorial geometry problems for you, okay? This is the only example for the notes. All right, now, last thing in our little tour here is, so this is kind of fun, is going to be, I mentioned last time, our combinatorial games, okay? So this is another important kind of branch of combinatorics. We're not really going to think too much about combinatorial games in this class because they're kind of hard to put in the, this topic is a little bit advanced. It's kind of hard to put in the general setting of most of the problems in this class, which will be counting a set, okay, a finite set. But nonetheless, this is an important branch of combinatorics, right? And so I think I mentioned last time what we mean by a combinatorial game. It's a very general definition, okay, for combinatorial games. So they are games, and many games that you're familiar with are combinatorial games, okay? So because the definition is very broad. So checkers, chess, tic-tac-toe, Go. The board game Go that's very popular is also that's a combinatorial game. I didn't mention, but I should have NIM. So I asked y'all, have y'all? No one's played NIM before in the class? Okay, now that's really unfortunate because NIM is a very good example of what's often true for combinatorial games. These are not. These are games, but they often have a lot of social and cultural significance and historical significance as well, okay? So chess clearly, right, has a lot of social and cultural significance, right, as an example of a combinatorial game. And so does NIM, okay, because it's very important in the history of computer science. So there are many famous examples of early computational devices that were special purpose computational, not many, but there are more than one example of special purpose computational devices in the early history of computing that were built specifically to play NIM, okay? I mean, that was their special purpose, all right? So it does occupy an important role in the history of computer science, but NIM also occupies an important role in the study of combinatorial games. So next time I will show you how to play NIM, okay? Really have to know that. Go, of course, is another game with lots of social and historical significance, also in computer science, okay, as well. You know, it was only recently, just recently, right, within the past few years, maybe a couple of years, that artificial intelligence researchers, right, have finally been able to write a Go program, right, that could beat the best Go player, okay, that was done several years ago for chess, okay, but Go is a more complex game actually than chess, and it's only recently that been able to write programs to play Go really well. All right, so here's what combinatorial games look like. So we're going to play some combinatorial games, not quite as hard as Go. All right, so a game is going to be combinatorial if it has two players. Got to have two players, okay? And I was thinking about I don't see why you can't have multiplayer combinatorial games, but they're usually restricted to two players. Maybe this is just to make the analysis easier, okay? So two players, and does not contain an element of chance or randomness. All right, so you cannot be rolling a die or drawing cards in a combinatorial game, okay? And the game does not depend on information that's hidden from one or more players. So card games, of course, are not combinatorial games because they involve an element of chance, right? Okay, but card games are also not combinatorial games because there's information hidden from one or more players, right? People have hands, you see, right? Okay, that they know that the other player does not know. In a combinatorial game, both players have all the information about the current situation of the game, right? Okay, the current status of the game. So, so that's the third condition. And so, generally now, let me see what I said here. So it's only those three rules, but let me see what I wrote here. Combinatorial games are not necessarily required to terminate. Oh, so you can have infinite, possibly infinite combinatorial games, okay, that maybe get, that for some reason or other actually don't terminate, okay? So the players can keep making moves. That kind of situation, for instance, can occur in Go, but there are special rules devised in Go to keep the game from being infinite, okay? So if any of you are familiar with playing Go, you have these situations called co-battles, right? And the rules of Go are devised so that you don't get caught in a but they can occur in chess, all right? So it is possible to play a chess game where there's infinitely many moves. Let's see, and also combinatorial games can end in draw. So of course tic-tac-toe can end in a draw, right? And of course chess also, but it's usually easier to analyze. So we're going to try to restrict ourselves to finite games so they don't get caught in the infinite loop, right? There's not a way to play the game where it extends infinitely, and you don't have a draw. Okay, so there's a winner and a loser in I think the games we're going to consider. All right, those are easier to think about. Okay. All right, so usually what we're interested in studying in a combinatorial game is if there's a winning strategy, okay? So does either the first player or the second player, there's only two players, right? So does the first player to move or the second player to move? Oh, in a combinatorial games, players alternate turns, right? That's also a condition. Players take turns in a combinatorial game. So player one is the person who starts and player two is the next player. So what we're usually interested in studying in a combinatorial game is, does one of the players, either the first one or the second one, have a winning strategy? That is there a system or a method that player can follow for choosing moves so that they inevitably win the game? That's a winning strategy. Okay, so that wouldn't be the case. Wouldn't be the case, right, for a tic-tac-toe, because sometimes tic-tac-toe can end in what? A draw, right? Okay. Yeah. All right. So, so in certain situations, right, it's possible to not have that neither player, right, can have a winning strategy. All right. So that's the basic question, right? Is there a winning strategy for one of the players? So you might think of this as, is the set of winning strategies for one of the players empty or non-empty, okay? I think a much harder question would be, how many winning strategies are there, right, for a particular player? Okay, now I'm going to let you all play a combinatorial game, okay? And then you're going to report back to me if you think there's a winning strategy. Maybe you know this game. All right. Now this one is kind of awkward the way it starts, because it starts in kind of a rote fashion, but then it gets a little bit more fun, a little bit. It's not a complicated game, right? So this is kind of like a elementary school combinatorial game. All right, but you might. Well, let's see what you think about it. All right, okay. So maybe you played this before, okay? This is the game Overboard. All right. So here's what happens. In this game. So again, it starts off in kind of a routine way. Players are going to take turns naming numbers, but there are rules for how they can choose numbers, okay? But player one has to start with 1, okay? So player one has to say 1, and then player two has to say 2, All right, so that's prescribed at the beginning of the game. And then on each turn, a player gets to pick a number strictly between the number that was previously chosen and its square. Okay, so when you get to the third turn of this game, that would be back to player one, right? Then player one can choose what their yeah, it's got to be between 2 and 4. So again, it's kind of wrote at this point, right? Adulted, it would have to be 3, right? Okay, yeah. Okay. Now this is where it gets a little bit more fun because now you're back to player 2, and player 2 then can pick what between. Is that right? Huh? Well, let's see what it. Let me remind myself of the rules there here. Oh, that's all I put. Okay, so yeah, between I thought it was between 4 and 16. Okay, ooh, I may have to check this again. All right, so the object. Let's see. So between 2 and 4. And then between 4 and 9.
It's between the number that was previously said and its square.
And it's square, right?
Three.
Yeah.
Because that's the only valid choice.
Right.
So it'd be between 3 and 9 then.
Mm-hmm. Okay. Well, let's play with these rules and see what happens. Okay.
Can you go up a little bit on the rules?
Yeah. Yeah. Okay. So that's it, right? Okay. Okay. All right. So what we're usually interested in determining here, right, is and now the first player that has to, so you have to have the game has to terminate, right? Okay, so it has to have a winner and a loser. So you lose if you're forced to choose a number bigger than 10,000, okay? Or it may be at least 10,000. Is that what it says there?
Yeah, I think it's at least 10,000.
Right, yeah. So the first person that has to say 10,000 or more, right, okay, is going to go overboard. So that's how you go overboard, and then that person is going to lose the game, okay? All right. So again, the basic question that we're interested in answering here is, does one of the players have a winning strategy? So is there a system or method, right, that the one of the two players can use for making moves, right, that will guarantee that that player wins, okay? Now, notice I'm being very general about what a winning strategy is. I just said it's a system or a method, okay, that player can use, all right? So system and method incorporates lots of techniques, okay, right, okay? But nevertheless, it's a method that sort of indicates to that given player what that player should do, right, in order to ultimately win the game, right? They have to ultimately know that they're going to win, all right? Okay? All right, so I want y'all to pair up and see if you can see what happens in this game. All right, so I want you to play a few rounds, right? Okay, it helps to switch players, okay, because the first part of this is kind of rote, right? So it helps to switch players and see who wins, right? Okay, and see if you can figure out what the right moves would be, right? Okay, to win that. Okay, all right. I need to check my rules, but it's not hard to find the rule. It's hard to find the rules for this game, right? Okay. So you've got to play it. That's right. I think that's the way it's played. I think my rules are correct. So, huh?
We can't pick the square, right? No. I'm saying.
Oh, yeah, no.
In the rules of
You can't pick the original number or the square.
Okay.
Yeah, that's right. It's got to be strictly between. Yeah, as I recall. Yeah, strictly between the previous number and its square. Right. Yeah. Pretty sure that's right. But if it's not, it's still a combinatorial game, so we can still see if we can discover a winning strategy. Right. Okay. Nah.
Try to get the biggest number closest to it, like 9. It has to be 10,000.
But you can still pick.
Yeah,
I think I know it.
10,000.
It's my turn, right? I have to pick in between 9,000.
It has to be in between.
Did y'all figure something out? Okay. All right. Hang on for a minute then. Okay. See if you can write it down in words, right? By the way, but Kaylee, a calculator could be part of a winning strategy
It could be, but you don't.
because you just need a system or a method. So if your system requires that I do something with a calculator, that's okay, right?
I don't think it necessarily be because it's 10,000 is 100 squared.
It is, right. Okay.
I guess the person who does it.
Yeah.
Oh, I see. So can you? All right. So if you, all right. So if you get a chance to say 99, right, you win. All right. So work backwards from there. What's going to guarantee you the chance, or what player is going to get guaranteed the chance of getting 99, right? Okay. Yeah. Right. Yeah. That's inevitable. Yeah. That's why it's kind of funky to start with, right? Okay.
Yeah, it can't be the number. Right, that's like. So I think if you do it like this, play it two.
No, the winning strategy cannot depend on the moves of the other player. It's got to be independent of their moves. So you cannot sort of luck into a win, right?
We can see how player one wins every time.
How player one wins every time? Oh, all right. Okay, so so it looks like the cat's out of the bag here. People have already said that they think there's a winning strategy for player 1. Okay, is that what y'all said? I thought it was player 2. Oh no, it's player 1, right? Yeah. Yeah. So if player 1 follows the strategy, player 2 has to lose. That's a winning strategy. Okay. So can y'all describe that for me? So what's player 1's method of making moves so that player 1 is guaranteed to win?
It's basically the first actual choice. Because they have to say 3.
Who has to say 3?
Player 1. Because 1 says 1, 2 says 2. 1 says 3, because they have no choice.
Right.
And then player 2 chooses between 4 and 8. Doesn't matter what they choose. Let's say they choose 4 first time around. Okay. So between 5 and 6, or between 4 and 16. You say 9.
Who says 9?
Player 1 says 9.
Oh, so player 1 winning strategy is when given the opportunity, do what?
Say 9.
Say 9, right? Okay. And then what?
And then whatever else they pick, it doesn't matter because anything squared will be over 100. So you just say 99 and you win.
Oh, I see. Okay.
100 squared.
All right. So player 1's sequence of moves is what? They would choose.
1, 3, 9.
Yeah. So when given the opportunity, do what? Choose 9. Right. Okay. Then 2 would have to pick between what? 10 and 100.
10 and 80.
Oh, I'm sorry. Yeah, 10 and 80, right? Okay. So then player 1 then picks what? 99, right? Okay. So player 1 moves are, what is it? 1, 3, 9, 99, and that's it?
Yeah, then 99, 99.
Oh, 99, 99, right? Okay. Oh, I see. Okay. So there's the winning strategy. That actually is a very definite winning strategy, right? That's exactly the moves to make, right? Okay. So there's almost no method, right, associated with that. Choose these 4 values, correct, and you are guaranteed to win. All right. So say these things, right? Okay. 1, 3, 9, 99, and 99. So actually 4 or 5 things, right, that player 1 has to say. See, that's a winning strategy. That's what I'm referring to. Okay, get the idea there? Okay. All right, let's try another one. Y'all had such fun on that one. Going to make it harder, though. All right, we may have to think about this one. All right, so this is the game Gridmaster. Maybe you know this game. All right, so this is typically played on an 8x8 chessboard, but you can make the chessboard smaller. It needs to be square, though. I think 4x4. No, it doesn't really need to be square. No, it doesn't need to be square. I'm sorry. Y'all know what it needs to be, actually. Okay, so it's typically played on an 8x8 chessboard, and on each turn, a player's going to place a domino on the uncovered squares of the board. Sounds familiar, right? Okay, and then the last player who can place a domino is the Gridmaster. Okay, so the first player who cannot properly place a domino has lost. So you might pick a chessboard with the size that guarantees a tiling, but in the game you don't really have to have a chessboard that you're guaranteed to have a tile. If you end up with some say one square left over, that person would lose because they couldn't place the chessboard. They couldn't place the domino. But if the board gets completely tiled, then the last player also then cannot put a domino on, right? They're going to lose, right? Okay, so but 8x8 has a tiling, right? Okay, so that's the game. That's it. It's just that simple. And so again, what we're interested in is, are there winning strategies, right? All right, try playing this one again, but don't try 8x8 because how many moves is that going to involve? A lot, right? 32, right? So you're going to have to play this a long time, right? Okay, so let's cut it down a little bit. Let's try maybe 6x6. That's still a lot of moves, right? So if you have some of my handy graph paper, right, just try putting a 6x6 grid there, and you'll have to color it in, right? Because we don't have dominoes. So play with your partner, right? Just make moves and see who wins. Okay. Now the winning strategy here is much harder to analyze. Okay, so I think the first time you play this, you're just going to be sort of randomly throwing dominoes out there, right? Okay, so who knows who's going to win, right? Okay, so the question is there a winning strategy? All right, I'm going to give you all a little bit of a hint though here, which is really useful. Any finite game that cannot end in draws has a winning strategy, believe it or not. Okay, they all have winning strategies. But describing the winning strategy is the tricky part, because, remember, a winning strategy can just be a method or a system. So it could be phoning a friend. You know, every time I have to make a move, I phone a friend. That's my method. Or it could be, that doesn't sound like we can guarantee that as a winner, though, right? Or it could be polling the audience, right? Okay, I mean, that could be your. The winning strategies can be very general, or it could be consulting a computer who tells me what move I should make. Okay, yeah, all right. So just try one play of this or something and see what. This will be basically who wins, right? Okay. The person who cannot place a domino. How can y'all tell? Can y'all tell what y'all are doing?
Well, I went second.
Oh, okay, because what happened?
Yeah.
Why? Oh, because you finished the tiling?
Yeah, she placed that last one.
Oh, okay. Yeah, so you lost there.
I placed all of mine one way. That's interesting. I didn't notice that.
That is interesting. So.
But he did his next time.
Okay. Well, did y'all at least figure out the game? I mean, did you have a winner and a loser? So, I mean, that's sometimes just the hard thing, is to figure out how to play the game.
Yeah. I mean, on your first game, that'd be technically a winning, one of a million winning strategies. So, or one of a million. Like the game they just played right now is technically a winning.
No.
There's a winning strategy in there somewhere.
No, that's not a strategy, right? The strategy is the method, right? But the method has to work in no matter what the second player does, okay? See, Dalton, did you win, Dalton?
No, I lost.
He lost. So Kaylee won, but Kaylee won, but perhaps because Dalton just because of the moves Dalton made, right? So if Dalton had played smarter, maybe Kaylee wouldn't have won in that case, right? Okay.
Will you player one or player two, Dalton?
Right.
Okay, I think I got it.
All right. Did y'all get? Okay, so this one's going to be much harder to analyze a winning strategy for. Okay, so I'll let y'all ponder Gridmaster. You might find someone to play it with you
Oh, here, I'll do a different one.
and see if you can become good at it. So we'll let y'all ponder that game for a little bit. There are two in the homeworks now and they're diametrically different. They're both easy to describe. Okay, so you have lots of combinatorial games like this one. This is kind of like Overboard, but maybe a little bit backwards. This is the game Cunan. So you're going to start from 15. And, oh, by the way, now in these games we have, it's like chess. We have the two players are white and black, and white is going to go first. All right. So we're looking for a winning strategy for white or a winning strategy for black, the second player. So in Cunan, you start from 15, and each player in their turn gets to subtract 1 or 2 from the current quantity, but you start from 15, right? So you can think of it as I have a pile of 15 coins, and I'm going to take out of the pile 1 or 2 coins on a turn, right? Many combinatorial games are described like this. And let's see, who loses there? The first person that hits 0 loses, okay? So we want to know is there a winning strategy for white, or is there a winning strategy for black, okay, with that game. I understand the game is very simple, okay? So easy if you have 15 objects to okay. I can probably analyze this one and figure out how to win this game, or who's going to win this game if they play properly, okay? Not that bad. All right, now the next one, tougher, okay? This is Poison Cookie. All right, so Poison Cookie is played on a 6x6 grid, so this is a grid game. And we imagine that in the bottom left-hand corner on the grid, there's a cookie that's been placed there, but it's poison, okay? All right, now, here's the way the game is played. So in turn, each player picks a square, okay? But, of course, you want to avoid the poison cookie, right? Because if you pick that square, you eat the poison cookie and you die. You're the loser, right? So so you pick a square, and then you get to eliminate from consideration all the squares above and to the right of that square, all of the squares. So you'll eliminate a whole rectangle of squares, okay? Not just in the column and in the row, but all the squares above and to the right, okay, on the 6x6 grid. Does that kind of make sense, Kaylee? Is this a 6x6 grid? Okay, so here's a 6x6 grid that they were playing on. So the poison cookie is here, right? So you don't want to choose the poison cookie. So player 1, for instance, might pick this square, right? But when they do that, then all the squares above and to the right are going to be eliminated, see? Okay, right? And then player 2 has to pick a square, right? Okay. Above and to the right.
Yeah, all the ones above it?
Yeah.
So wouldn't that include the ones?
No, above to the right. So it would be this this quadrant. It gets eliminated, right? Okay, yeah, like that. So, player 2 could pick here. It wouldn't do much. That would just cut off these, right? In addition to the ones that were already. So the person who has to pick this square, the lower left-hand square, has to eat the poison cookie, right? They're the loser of the game, okay? So the question is, how do you play that game? Yeah, what makes it good? How do you play that game good? And who has a winning strategy, right? Does somebody have a winning strategy? And if there is a winning strategy, can you describe that? Okay, that's a good game to think about. Okay, but harder to analyze. All right, so don't beat yourself up too much if you don't get good at playing poison cookie. Okay, all right. All right.
We have to become experts at beating ourselves.
No, get someone to play poison cookie with you. Okay, so you can have a poison cookie tournament down in the honors lounge or something, right? Okay, and maybe the prize will be a non-poison cookie, right? Yeah, if you win the tournament. Okay, well, we're not. 4 minutes. Let me quickly here. So I won't run over. Let's quickly here mention. I just want to know answers. See what people got. So, what did on these problems? What did y'all come up with for? Do y'all remember this problem 5? That was how many tilings are there of a 3x4 chessboard? What did y'all get? Anybody got that? You got 12? I got 9, but I was wondering how off I was because I only thought about it for about a minute or two. So
I know there's at least 10, I think.
we don't have a consensus here.
I think at least 10.
I got 11.
Okay, all right. So some people, I got an 11. What else do we have here?
We have a 10 and a 12.
We have a 10 and a 12. So, and I got 9. So somewhere between 9 and 12. Wow, we have to nail that down. Okay, so somewhere between 9 and 12. All right. Well, you have to turn this in. So I'm gonna have to think about that. Okay. All right. But now, the thing that, well, it's too late. So because you're turning it in, right? The thing I was going to keep in mind is you may think you have 2 different tilings, right? But they through the system that you're using to count. But remember, your system may duplicate the same tiling twice. I think that may be what have happened if you got 12. But I could be wrong. I just could be wrong, right? That's possible. What about 3B there? So how many ways can we paint that 6-sided die? What are we painting it with? Oh, this is the one where I repeated the problem, right? Is this the right version?
Oh, no, one's a die and one's a cube.
Yeah, one's a die and one's a cube, right? So there's a die and we're painting it red or blue, right? Okay. What'd y'all get there? Is it 64? 64, I think, is right. 2 to the 6th power, okay? So 2 to the 6th power, 64 is the right answer there. So if you got that, you got it right. This is a type of problem now that we're going to be able to develop formal methods for solving. So we're going to do that really quickly, okay? That's what we're up to next, all right? So we're not having to exhaustively count all of these 64 colorings. How can we quickly count this set? This is a much harder one. Where we paint one black and then the other red or blue, but it's not a die, right? It's just a cube. So the, oh no, this is a die, right? Okay. So one is painted black and the other are painted red or blue. Did y'all get an answer to that one? 192? Oh, wow, okay, that's impressive. So 192? Okay. So this is somewhere between 9 and 12. This one was 64. We have several people agreeing with 192 there. Nice. Okay. All right. What about this one then? Not a die, just a cube. So the faces of the cube are not numbered like they are in a die, right? So it drops dramatically. What do we get there? 8, 6, 10, 32. I think you're all wrong. I think the answer is 12. What becomes hard in this? What makes this problem hard? The orientation does not matter, right, okay? So it's really just the relationship of the colors to one another, right, okay, that's really important. So you have to have a little bit of spatial sense here to answer this question. I think the answer is 12, but maybe I'll have to double check that, okay? All right, so I'm looking forward then to recomputing that. What about this question then? where you're trying to build the tour and you're going through each door once, right? And you have to start and end in the same place, right? Outside. So how big is T there? 0, right? Okay. So there's no way of doing this. This is a famous puzzle of Euler, like the 36 officers problem. Okay. Yes, that's the bridges of Königsberg. This is not the bridges of Königsberg, but it's the same problem, just restated. Okay. And how do you fix that? So what if this door that is on the inside is moved to the outside? What happens then? Oh, someone actually counted that? What'd you get, Kaylee? 16? So that's hard. But it's certainly more than 1, right? Okay? So this set becomes non-empty, right, when you move that door, all right? So Kayla says it's really 16.
Well, I was really tired by the end.
And you were just doing that by exhaustively sort of considering the possibilities? Yeah. All right. So that's what we're trying to get away from. I wonder if that's right. That's what we're trying to get away from is, trying to exhaustively consider possibilities, right? So we're trying to find systematic methods for counting these sets where we don't have to go through this exhaustively counting the possibility. That's what we're going to learn about next. We're going to start with some very, very elementary counting problems, though, so elementary that you're going to think, my God, what have I gotten into? This is like, it's like kindergarten, right? Okay. Oh, you just gave up at 16? Okay. Yeah, that's probably what I would have done too, right? Okay, is give up, right? There's a lot, right? Okay, certainly more than 1. And that's the problem with trying to exhaustively count all the possibilities, right? It's just really hard to do. It's just really hard to keep track. So we're going to start with some very elementary ones, but the point of the very elementary problems is to understand the techniques that we're using, right, and try to get those really fixed in our minds so that we can, use those techniques on harder problems, right? But first we have to understand the techniques really at a very basic level so that we can apply them to harder problems. So we're going to start with very basic problems, but try to apply the techniques very rigorously to the very basic problems. That's my goal. All right, okay, so this will seem much easier next time, right, than these first 2 homeworks. Okay. All right, so we're done. Oh, ran over. Sorry. Bye. Go away. Another class is waiting. Oh, just set those somewhere. Your homeworks, yeah? Okay.